Okay, lecture 46. Consider the reaction. So we have this reaction and involves a gas. How many mils of chlorine are produced when 56.7 grams of manganese 4 oxide is reacted with at 788 millimeters mercury and 41 degrees Celsius? So because we have the ideal gas law, which is PV equals nRT, that N gives us moles, and once we're in moles, we can use the ideal gas law along with a reaction that involves a gas. Has to involve a gas, because the only thing here, let's see, aqueous, solid, the only thing that has a pressure is that chlorine. It's the only thing that has, well, the others have a volume, but the only thing that has a volume that can change significantly with pressure or temperatures is the chlorine. So what we're going to do is what we have done in chapter 3. We start with grams and move over to moles, but then we're going to change to volume. And so it's a little different. It's a lot like the chapter 3 problems, but we have to do an extra step. So how many mils of chlorine are produced? So we have 56.7 grams of manganese oxide. We need to get this in terms of moles of chlorine, and then we can use the ideal gas law to find our, what are we after, a volume. So manganese is 54.9 plus 32. So this is about 87 grams of manganese oxide is 1 mole of manganese oxide. We look at the equation, 1 mole of, actually don't need, just 1 mole of manganese 4 oxide equals 1 mole of chlorine. And that's as far as we need to go. That will give us our number of moles of chlorine that were produced. So 56 grams of manganese 4 oxide divided by 87 produced 0.652 moles of chlorine. If this was a chapter 3 problem, we'd convert this to grams, we'd be done. But since it's a gas, we don't normally deal with masses of gases because they float above the above our balance. The balances that we try to use. So we usually go with either pressure or volume. So since this is N, and they want to know the volume, so we take our ideal gas law. Number of moles is 0.652. I didn't leave myself a lot of room here, so let's see what we can do. This is 0.0821 liters atmospheres per kmol. The temperature is 41 degrees Celsius. That's 314 Kelvin. And the pressure is, of course, don't give myself any of the proper units, that's fine, 1.04 atmospheres. Moles cancel, K cancels, atmospheres cancel. Things looking just dandy. And we get 16.2 liters. And let me double check that. That's 314 divided by 1.04, 16. And then they want mils, so we have to convert that. That'd be 1.62 times 10 to the 4th mils for our answer. Look at the second problem here. 256 mil of chlorine is produced at 1.05 atmospheres and 35 degrees Celsius. How many grams of water are produced? Now we have to go back the other way. We have to find moles, so PV over RT. And then once we have moles of chlorine, then we go back to our chapter 3 kind of thing using the equation. So the assumption, since it's part B, it's the same equation. So the pressure is 1.05 atmospheres. The volume is 0.256 liters, 0.0821 liters atmospheres per kmol. Temperature is 35 degrees. I think that's 308, but I'm going to do it out. I don't know if I'm sounding kind of surly, but up in my office, my house, and it's in the middle of summer. It's got to be, even with the air going, it's got to be 85 degrees in here. So we have this many moles of chlorine. I'm going to double check that. 1.05 times 0.256 divided by 0.0821 divided by 308. And now that we have moles of chlorine, we can go to the equation. 1 mole of chlorine, what are we trying to find? Water is 2 moles of water. And 1 mole of water. So back to chapter 3 stuff, 18 grams. So 0.0106 times 2 times 18, we get 0.382 grams of water. And just double check that. Times 2, because it's 1 to 2. I didn't show the equation, but it's earlier there. I'll show it in a second, in case you. And so using this equation, we go back and we find, we use the volume and the pressure and the temperature to find number of moles. And then now we can use the equation to find the grams of the other species. Here's another set here. We have how many liters of bromine are reacted when 7 liters of bromine trifluoride is produced at STP. Here's the thing that's important. When we're at STP, well, actually, when we're dealing with gases, the volume, since we're at the same temperature and pressure, we can assume that the volumes are the same. It's one volume, or in proportion, I should say, and one volume. So instead of, we can certainly use STP and the volume to determine number of moles and then convert to moles and then back to volume. But since they're gases, we have that nice little thing going for us, that we have 7 liters of bromine trifluoride. For every volume of, I should say this is exact, so 1 liter of bromine trifluoride, that is produced, 1 liter of bromine is reacted, so it's 7 liters. So gases give us this nice little shortcut. As long as we're at the same conditions throughout the reaction, then the volumes can be used as we used moles. So nice and simple. That one caught me off guard. I forgot that's why I put it in there. And then how many mils of fluorine are reacted when 115 grams of bromine trifluoride is produced at STP? Okay, so there's a couple of ways of doing this. I'm going to do this out first as the regular type of problem. We have to convert to moles. So bromine is 80 plus, we get 137 grams. That STP also gives us another route to take for solving this. And it's in the more complicated problems, the more ways of doing the problems. And I'd focus on just one type first. I'll show you this other type here in a second. We have this many, 1 mole of bromine trifluoride. What do we after fluorine? Is produced when 3 moles of fluorine react. And so we have moles of fluorine. So 115 divided by 137 times 3. So 2.52 moles. And that STP has been mentioned before. It's in your book. So if you aren't clear on what that means, go back. The standard temperature and pressure, 0 degrees Celsius, 1 atmosphere. So when you see STP, you should be able to work with that immediately. So this is our N. Our pressure, so we're trying to find, what are we trying to find? Volume. So it's nRT over P. Our moles are 2.52. Our gas constant is this. Our temperature is 0 degrees Celsius, so 273.2, we'll just say 273. It can be 0.15, but that's going to fall away anyway with the rounding. Our pressure is 1 atmosphere. So the STP makes our life a lot easier. We have 2.52 times 0.0821 times 273 divided by 1, so this is 56.5 liters, and that would be 5.65 times 10 to the 4th mils. Now, another way of doing this, we know that at STP, hopefully I have enough room, at STP, 1 mole of gas, any gas, equals 22.4 liters. That's the standard molar volume at STP. So if we need to find the volume, well, we found the moles is 2.54. And I'm going to just do the calculation up here. Yeah, we'll do it down below. I think I have enough room here. So all we have to really do at as long as it's at STP, it has to be STP, we just take the moles, and we know that it's 22.4 liters per mole. That's the standard molar volume. And it might be slightly off because of rounding, and we end up with 56.4 liters. Here is 56.5 is what, and just rounding error, and then that would be 5.64 times 10 to the 4th. So if you're aware of that shortcut you can take when we're at STP, STP helps us out a lot. Even when we can't do this, it's 1 atmosphere, which is always helpful for the calculations. But as long as you know that 1 mole of gas, any gas at STP is 22.4 liters, that can help you find the volume a lot quicker. If not, you have to go through this whole process. Fine, an extra minute worth of work, but it's nice to know that shortcut.